In this problem, we have a 75 kilogram man who is pushing on a 150 kilogram crate with a horizontal force F. We are given both the coefficients of static and kinetic friction between the crate and the surface. And we are also given the coefficient of static friction between the man's shoes and the surface. We need to first determine if the man is able to move the crate, and also what is the greatest acceleration the man can give the crate if he indeed can move it. So in order for the man to move the crate, that is when the static frictional force between the crate and the surface has reached the maximum limiting value. So if we do the free body diagram of the crate, subjected to its weight, which is 150 times 9.81, which is 1,471 Newton. And then because there's no inclined surface, so the normal force can be easily determined from the equilibrium along the vertical direction to be the same as the weight. And then this person is pushing the crate in this direction, therefore the tendency of motion is to the left. As a result, the friction tries to resist that movement, so this friction of the crate is to the right. Now, when the crate is about to move, the friction reaches the limiting static friction, which equals to mu Sn. In this case, that is 0.3 plus multiplied by normal force 147.1.5, and that equals to 441.5 Newton. So that is when the equilibrium of this crate is about to be over. Okay, so at that limiting moment, at that limiting instant, we still have equilibrium along the x direction, along the horizontal direction, because equilibrium is about to be broken. But at this point, we still have equilibrium along the x direction. Therefore, resultant force. So this is my conventional x and y axis. Resultant force along the x direction equals to the frictional force 441.5 minus F equals to 0. Therefore, we can easily determine that F equals to 441.5 Newton. So how do you interpret this? This is the force needed to move the crate. So this is the force needed to make the crate start sliding. On the other hand, if we look at the person, because this person is pushing on the crate to the left, therefore there's a force, action and reaction, to the right acting on this person. And he is of course subjected to its own weight, which is 75 times 9.81, which is 735.75 Newton. Also, a quick equilibrium analysis along the vertical direction, the normal force must be the same as the weight. And because the force acts on him is to the right, therefore there's a frictional force to the left, trying to resist that tendency of motion of this man. So in order for this man to move, this frictional force also has to reach the maximum static friction for the man, which equals to mu S man times N, which equals to 0.8 times 735.75, and that equals to 588.6 Newton. So again, if we do a quick force analysis along the horizontal direction, we can see that F this force right here also equals to 588.6 Newton. This is at the instance that equilibrium is about to be broken. So how do you interpret this? This is the force needed for the man to slide to the right. So if the force, the reactive force acting on the man exceeds this value, this man will slide back to the right. And that's when this man is not able to move this crate to the left. So if we compare these two forces, you can see that if I call this F prime, you can see that F prime is smaller than F, bigger than F. In other words, you need more force to make the man slide than the force needed for the crate to slide. Okay, so you need less force for the crate to slide. You need more force for the man to slide. Therefore, the conclusion is, do it in, yes, he can move it. So that's the conclusion for the first part of this problem. For the second half of the problem, what is the greatest acceleration the man can give the crate? We have determined that the greatest force that can act on the man without the man sliding is 588.6. Therefore, this force is also greatest force the man can use to push the crate without himself sliding. Therefore, because of action and reaction, in this scenario, if we draw the free body diagram of the crate again, in this scenario, the force the man is going to give the crate is the maximum static frictional force for the man, that is 588.6 Newton. So he's still subjected to the weight, still subjected to the normal force. These two forces balance out anyway. But now, this force, because it is bigger than this force, therefore the man is making the crate slide. Therefore, the frictional force now is kinetic friction. And kinetic friction equals to mu k times n. In this case, it equals to 0.2 times the normal force, 735.75. And this kinetic frictional force equals to 294.3 Newton. And now we're going to draw the kinetic diagram for the crate. The kinetic diagram is simply m crate times a, which is 150 times a. So if we assume this is my x prime direction, so I'm summarizing the forces along the x prime direction. Resultant force along the x prime direction, which is positive to the left, this equals to 588.6 minus kinetic friction, 294.3. That equals to 294.3, and that equals to, according to my kinetic diagram, 150 times a. So from here, you can solve for acceleration. A equals to 1.96 meter per second squared. So that answers the second half of this problem.